let's start off with the definition. What is a potentiometer in the first place? So as you can see from the name itself, it is a meter that measures the potential. So it is a device, electrical device, that is used to measure potential, or you can say voltage. And if we be more precise, we can say an electrical device used to measure EMF of a battery. So primarily it is used to measure EMF of a battery. So I'm going to write over here an electrical appliance to measure EMF of a battery. All right, and with this device, if you're going to measure the EMF of a battery, we have to compare it with the EMF of another battery, and the EMF of that battery, the other one, has to be given. It has to be known. Only then we can make use of the potentiometer. Now, potentiometer, I mean, in real life, it is used for many purposes. For example, you can control the speed of the fan using the potentiometer. So in electronics, potentiometer has different purposes. But for physics, A-level physics syllabus, the main purpose of potentiometer is to measure EMF of a battery. Now you might be wondering, why can't we simply measure the EMF of a battery using a voltmeter? So let me draw a voltmeter over here, and let me draw a battery. So for example, this is a battery, but we have studied that a battery has internal resistance as well. Now this collective thing would be called as a battery. This collectively is your battery that has some internal resistance as well. So let's say this is a EMF of the battery, and there is the internal resistance of the battery as well, which is R. And now you want to measure the EMF of the battery. And what you do is you say, let us simply connect a voltmeter. Okay, so I'm going to connect a voltmeter, and voltmeter is connected in parallel. So we are going to measure the terminal potential. Whenever we have the internal resistance in the circuit, whenever we have the internal resistance for the source, do you remember what is the formula to find the voltage, to find the terminal voltage? So I'm going to write down the formula, and you can just confirm if it is correct or not, or if you have studied this or not. V equals to I minus IR. Okay, so we studied this formula in internal resistance. Whenever you have the internal resistance, so this is a formula that relates the potential difference, the EMF, and the internal resistance, and the drop at the internal resistance. Now the question is, the reading that you get on the voltmeter is not the EMF of the battery. It is the terminal voltage after subtracting the drop at the internal resistance. Because in this case, as the current flows through the circuit, as the current flows through the battery, through the voltmeter, only then you get the reading of the voltage. So that reading would be the terminal voltage, and let's say the EMF were 9 volts. Okay, let's just assume EMF were 9 volts, but there would be some drop in the internal resistance as well. There must be some drop in the internal resistance as well. So let's say 0.5 volts. So what is the reading that you get on the voltmeter? On the voltmeter, you'll be getting 8.5. So you'll never be able to know what is the actual EMF of the battery. What you'll be getting is the voltage after some of the voltage has been lost in the internal resistance, not the actual EMF. So that's why we have this device which is called as potentiometer, and it can measure the EMF without the voltage being dropped at the internal resistance. Now the question is, how can internal resistance not be dropped in the battery? How can the voltage in the internal resistance not be dropped? Well, this thing IR has to be 0. If IR is 0, it means no voltage would be dropped in the internal resistance of the battery. In order to make IR 0, either the current has to be 0 or the internal resistance has to be 0. And the fact of the matter is, internal resistance cannot be 0. Matter of fact, you cannot even change it. If it is 50, let's say if it is 0.5 ohms, it'll remain 0.5 ohms. So what we can do is, if we come up with a device for which no current would flow through the internal resistance, so IR would be 0, hence the voltage drop at the internal resistance would also be 0, only if current is 0. And that kind of condition, when no current flows through the internal resistance of the source of the battery, for which we need to find the potential, for which we need to find the EMF. In that case, we say potentiometer is balanced. Okay, but we'll explain each of these pointers in the sample questions, in the examples and the sample questions. So let me write down the second important point. It is made up of, made using 1 meter long, generally 1 meter long. Okay, it could be more than that, slightly less than that, but generally 1 meter long nichrome wire. Okay, so up next, I'm going to draw the simplest diagram for the potentiometer. And here we go. So first of all, let me start off with the battery. The given one, a battery for which we know what is the EMF. And then you have a load. You can call it a resistor. Looks something like this. And let's say this is your wire, 1 meter long, from X to Y. Okay, X to Y, we have a wire which is 1 meter long. Okay, so I'm going to explain the movable terminal first. So for example, if I connect a voltmeter over here, okay, so this is a voltmeter. Now one end of the potentiometer is movable. We call it movable junction. We call it pointer. And this one is movable. And let's call it the pointer K, the point K. And this could be a resistor. It could be any appliance. It could be a load. Now the basic principle is, if we adjust the position of the pointer K, we'll be getting different readings on the voltmeter. This is the most important point. If we change the position of the, the pointer K, we'll be getting different reading on the voltmeter. Okay, and in order to make it even simpler, let me just connect this point over here, exactly at X. Technically, it's just the same thing, but just for your convenience, I'm going to connect it at X. So if I change the position of the pointer K, I will be getting different readings on the voltmeter. And let's see how the readings vary. So the first thing is, if I bring the pointer towards the point X, if pointer K is moved to X, meanwhile you can keep noting it down as well. If the pointer K is moved to X, voltage will be 0. And then the question could be why? Why the voltage reading would be 0? Because the voltage is proportional to resistance. All of it were 1 meter long. From X to Y, it was 1 meter long. And voltage is proportional to resistance. And then resistance is proportional to length. And if the pointer K is placed at X, it would look something like this. Then the next question would be, if the pointer K is placed at X, exactly at X, what is the length of the nichrome wire that you have used? Or how much length of the nichrome wire you have used? The answer is 0 meters, because both the points are at exactly the same point. So if you have not used any of the part of the nichrome wire. So what happens is, the length you have taken is 0, hence the resistance would be 0, and eventually if the resistance is 0, the voltage would also be 0. Okay, then so far so good. Let me change the position of the pointer K. So this time around, I'm trying to move the pointer all the way to the position Y. Let's see what happens now. So if pointer K is moved to Y, if the pointer K is moved to Y, then the voltage would equal whatever maximum voltage is possible at XY, between XY. So you'll be getting the maximum possible voltage. And once again, the question is why? Why this time we get the maximum possible voltage? Because this time around, you're using the entire length of the nichrome wire. You see, one of your point of the voltmeter is over here. The other terminal of the voltmeter is over here. So what does that mean? You have used the maximum length. Hence, you'll be facing the maximum resistance. And if you're facing the maximum resistance, there would be maximum voltage drop, and you'll be getting the same maximum reading on the voltmeter. So by adjusting the pointer K, we can get different readings on the voltmeter. Now let me just replace the voltmeter by a filament lamp. So if I just replace the voltmeter by a filament lamp, and I start off by placing the pointer K at X. So as you move the pointer from X to Y, okay, this was the point Y, and we have placed the pointer K all the way to the pointer X. Now the question is, if I slowly move the pointer from X, I start off with the position X, and I keep moving the pointer all the way towards the point Phi gradually. What do you see on the filament lamp? What would be the effect of it on the filament lamp? I think you might be trailing. You probably need to refresh. At the position X, the voltage around the filament lamp would be 0. You won't be getting any voltage. The voltage would be 0 around the filament lamp. So if the voltage is 0, it would be getting 0 current, and the filament lamp would not be even switched on. And as I move it towards the right side, let's say if I move it from here, if I move the pointer K from here to some place in the middle, now the filament lamp would be getting some voltage, because this time around you have used this portion of the wire, let's say 20%. So there is some portion of the wire that is used, hence there is some length used, there would be some resistance, and there would be some voltage across the lamp. So this time the brightness of the lamp would increase, and if I move it all the way to the point Y, that would be the point where the brightness would be maximum. So it would be actually the other way around, the brightness would increase. So are we clear with this? How do we measure the EMF of a source using the potentiometer? So you can note down the steps afterwards, but let me just show you the explanation. And matter of fact, in practical, in your physics lab, if you take a look at the potentiometer, it would look something like this. So the movable portion that you can see is kind of your pointer K, which you can move around. So in this one, what we're going to write is, if in the diagrams you're shown this condition, the galvanometer is shown in the vertical position, it means no current through the lower circuit, means this one circuit, no current through this one, and this position of the galvanometer is called as balanced position. So your galvanometer would now be known as in balanced state, or galvanometer is balanced. They'll simply say the galvanometer is balanced. It means no current is flowing through the galvanometer. Oh, sorry, not the galvanometer. They'll say the potentiometer is balanced. And they can also say the galvanometer is balanced. Means no current is flowing through it. Now let us take a look at the most important thing. Matter of fact, this is why we study potentiometer in A levels, which is to find EMF of a source using the potentiometer. Now, in order to use this method, you have to have a battery for which EMF has to be given. For example, in this case, we have connected a battery in the upper path for which EMF is given, which is V1. Let's say it is V1. And then there's a battery on the lower side, you can see, for which the EMF is unknown. Let's call it V2. The EMF of this battery is unknown and we need to find it. Now the key idea is, obviously then I'll show you the slide where I've written all the steps, but just try to understand the key idea behind it. If somehow we are able to keep the potentiometer in a balanced state, which means no current should be flowing through this galvanometer. If no current flows through this galvanometer, then that would mean the voltage over here equals to the EMF of the battery. So let me repeat this statement once again. If the potential difference over here, whatever the voltage is between X and T, if that voltage equals to EMF of the battery, then no current would flow through the circuit. So let's say if the voltage across XY is, let's go with 5 volts. Okay, let's say if the voltage across XY is 5 volts and no current is flowing through the galvanometer at this position, if the movable pointer is placed over here and no current is flowing through the galvanometer, then that means the unknown battery is also of 5 volts. And that's pretty much it. So what do? We keep changing the position of this terminal until the galvanometer reads no current. So if the galvanometer is at null position, until or unless the galvanometer moves to a null position where it shows no current, we keep changing the position of the terminal T. And eventually, at a certain position, the potential difference over here, which I assume, let's say 5 volts, if that potential difference equals the EMF of the lower battery, the unknown battery, only then no current would be flowing. And you know this thing already, because current equals to potential difference over resistance. What is this voltage? It is basically the potential difference. If there is no potential difference, no current flows through the circuit. So it is basically the potential difference that causes the current to flow. The very simplest example is, you might have seen the birds sitting on the transmission lines. Okay, so you might have seen the birds sitting on the transmission lines. So these transmission lines, they carry very high voltage. It could be like, let's say 13 kV transmission line. So it contains 13,000 volts. And yet the bird that is sitting on the transmission line is not electrocuted, which means it does not get the electric shock. The reason being, the body of the bird and the transmission line, they get at the same voltage. So if these two things are at the same voltage, current would not flow. In matter of fact, the current would flow only if a certain part of the bird touches this wire, and the other part of let's say, other body part of the bird touches the neutral wire. The neutral wire is at 0 volts. Then you have the potential difference. How much? 13 to 0, it would be 13,000 volts. So that potential difference would be disastrous. And if you're at the same potential, no current would be flowing. So this is exactly the same principle we use in the potentiometer. So what do you write on this one? Just let me open up that slide. So here we have, and now you can see it's exactly the same thing I've explained already. Potential difference across wire between points x and t means these points, between these points, is adjusted to balance out the current of E2. And how do we do that? If the voltage across xt equals to the EMF of the battery, the length between x and t is adjusted to change potential difference across E2. So you know this thing, if I remove it from here and I connect this terminal over here exactly at x, what did I say then? The potential difference across xt would be 0, and the current would start flowing through the galvanometer, because this time the potential difference is not same. So at this one is the most important thing. At a specific length, this voltage would equal to EMF of the battery, and then the galvanometer would read no current, and all we have to find is what is the voltage at this point between x and t. How do we find it? Using the ratio method, and I'll explain how do we find that using the ratio method as well. So you can just take a screenshot of it, write it afterwards. It's exactly the same thing I've mentioned. So let's move on to the sample questions. So here is the first example, and let me erase it off. So in the question reads, the galvanometer is in a balanced state and you have to find the length xp. Is in null state, means zero current through the galvanometer. You have to find length xp. So basically you need to find the length at which the galvanometer would be balanced, or at which the potentiometer would be balanced. So what do we do in this question? So you see, first of all, we know this thing, that the voltage across x and p, if we just take any voltmeter and we try to measure the voltage across x and p, that voltage would be 1.5 volts. Because only if the voltage between x and p, equals to the EMF of the battery, only then the current through the galvanometer can be 0. Otherwise the current cannot be 0. So that means if this EMF is given, okay, so in this case the EMF is given. Generally we use the potentiometer to find this EMF, but in the question they can ask you for anything, and I'll explain all with the help of at least 5 examples. So let's say the EMF is given, but what they're asking is at what length no current would flow through the galvanometer. So what do we do in this one? So first of all, you say that if the galvanometer is reading no current, it means whatever the voltage is over here, that should also be between the points x and y, because these two points are connected in parallel. How do we know the points are connected in parallel? If their left ends and their right ends are connected directly. So think about it. The left end of x is connected with a positive. the right end of over there is connected to the negative. And there would be, matter of fact, there would be no voltage drop over here. Because you might be wondering that out of 1.5 volts of the battery, why do we not have the voltage drop in the internal resistance? So let's say the voltage drop in the internal resistance is 0.5 volts. Then we should be getting 1 volt over here between X and P. So there has to be at least some voltage drop inside the internal resistance, and the leftover voltage should be across X and P. But that's not the case here. In this case, there is no voltage drop in the internal resistance of the unknown battery. Just to assist you, I'm going to write down the formula. Now V equals to I minus IR. This is the formula that we use whenever we have the internal resistance. Whenever there is a concept of internal resistance, we use this formula. So V is the voltage that you get across the point X and P, and E is the EMF of the battery. But there has to be some voltage drop across the internal resistance, which we are saying is there won't be any voltage drop over here. So how do we answer this question? Why there is no voltage drop in the internal resistance? So hint is in this equation. Yeah, what equals current through the internal resistance is 0. Matter of fact, current through the battery is 0. So no current passing through the internal resistance, no voltage drop. And this is precisely the advantage of using the potentiometer. It can give you the value of EMF of the unknown battery without drawing the current through it. This is why it is preferred over the voltmeter. So never just a separate question, but let us solve this one now. What do we need to find is, we need to find at what length these two values are equal. So let us consider the upper circuit first. The upper one. Okay, and I'm going to erase off all the extra stuff from here. So you see in the upper circuit, the 2 volts, if I consider this circuit only, think about it. This one only. The 2 volts are provided, will be provided all the way on the wire XY. So think about it, the wire XY just as a resistor. So you have 2 volts over here in the upper circuit. I'm going to draw the upper circuit in a simpler way. So just consider the wire XY as a resistor, and the resistance is 1 meter. So 2 volts are provided across the wire XY, which is 1 meter long. So what you need to find is, if the length is, what would be the length for which the voltage would be 1.5 volt. So for 2 volts, the length is 1 meter. And for what length? The voltage would be 1.5. What do we do? Cross multiply. So you write, let's say, voltage over here, and you write length over here. Okay, voltage on one side, length on the other side. So when the voltage was 2 volts, it was across the length 1 meter, or for 1 meter length the voltage is 2. And if the length is unknown, xp, you can write xp here, or the length is unknown, for what length the voltage would be 1.5. And we know the voltage across xp would be 1.5. How do we know? Because the EMF of the battery is 1.5. And why should this one equal to EMF of the battery? Because the current is 0. And from there you simply cross multiply and you get the answer 0.75 meters. So this is the first variation. Let's take a look at the other one. So in this one, we have placed an extra resistor which is of 1.0 ohm. And the question is once again the same. Find length xy. That needs to be found out. Now the first question is, what is the voltage across point, or voltage between the point x and y? What is the voltage, or what is potential difference between the point, not xy, sorry, between the point x and p? What would be the potential difference between the points x and p? 1.5 volts. And how do we say that? Why 1.5 volts?
Because the
Is exactly right. And why does the voltage between xp, why does it has to be equal to EMF of the battery? Because the current, it is given in the question, because the current through the lower circuit, current through this one is zero. No current is flowing through this one. Hence, there would be no voltage drop across this resistor. And you see, then how is this question different from the other one, from the previous one? We have an extra resistor over here. But once again, the thing is, this resistor is, you can say, redundant. It's not even used. Because since no current is flowing through the lower circuit, there would be no voltage drop across this resistor. If you try to, let's say, find a pathway for the current, I start the current, let's say, from this side. The current flows through here, goes through the resistor, goes to the point X, comes to the point P, and goes through it has to go to the other part of the battery now. It goes through the galvanometer, but the problem is there is no current in the galvanometer. So we'll have to say no current is flowing through this resistor as well. So what does that mean? It means the voltage across xp is also 1.5 volts. And if you need to find the length, just use the ratio method. So volts over here, length over here. So for 2 volts, if the length was 1 meter, it was getting 2 volts. And if the length is xp, which is, let's call it x, it would be getting how many volts? 1.5. And the answer to this one would once again be 0.75. So let's move on to the next one. Case 3. There is an additional resistor in the upper circuit. So now the thing is, these 2 volts, which for the upper circuit, the points V and Y, the potential difference, sorry, the point X and Y, the potential difference across X and Y, which was previously 2 volts in the other 2 examples, this time around it would not be 2 volts. The potential difference between X and Y would no longer be 2 volts. And matter of fact, this resistance, you cannot say there is no voltage drop across this resistance, because there would be. This resistance, some current flows through this resistance. So let's say if you try to find a continuous path, the current can flow through here. So there would be some voltage drop across this resistor. How do you find it? Cross multiplication once again. So we'll find, and even before that, if this voltage is 1.5 volt, between X and P, it would be 1.5 volts once again. How do we know that? The voltage at X and P should equal EMF of the battery, the lower one, let's call it E2. Why? Because no current flows to the galvanometer. But what we need to find is, we need to find what is the voltage across X and Y. So if I just convert the upper circuit, just take a good look at this one. I'm going to convert this thing into a separate circuit. So it will look something like this. The resistance of the wire from X to Y is given. It is 5 ohms. and you have 1 ohm over here, and this was a point X, this was a point Y, and the resistance from X to Y is given 5 ohm for all 1 meter. So how much voltage would the wire XY be getting? How many volts out of 2 volts would be provided to the wire XY? Cross multiplication. So you will write volts on one side and you write resistance on the other side. So the 2 volts would be collectively provided to 6 ohms. The total voltage would be provided to the total resistance. Then for 5 ohm resistance, how many volts would be provided? And the answer to this one would be X equals to, I think, 1.8, 1.666, so 1.67. So the overall voltage that XY is getting is 1.67 volts. 1.67 volts. Now, how many volts? Okay, we have found that. So now we need to find the length XP. So let us use cross multiplication once again. You write volts on one side and length on the other side. Now the 1 meter wire, this time it's not getting 2 volts, it's getting 1.67 volts. Then for what length, you can write XP. For what length, the voltage would be 1.5. And then you can find the value of X, which in this case would be 0.89, or you can write it as 0.90 meters. So the length of between the points X and P is 0.90 meters. So let's consider the next case. So here we have the next case, case 4. So how is it different from the previous two? From the previous 3? You have a resistor 1 ohm which is connected in parallel to the battery. Now the first question that you ask to yourself, would there be any current passing through this resistor? Provided no current should be flowing through the galvanometer. So if no current flows through the galvanometer, would there be any current passing through this resistor? And from the upper circuit, we know that out of these 2 volts, no voltage would be dropped because we don't have any resistor over here. So no voltage would be dropped, and all of the 2 volts would be given to XY. So the voltage between the points, the potential difference between the points X and Y would be 2 volts, just like the example 1 and example 2. Unlike example 3, because over there we had a resistor across which some of the voltage was dropped. But then let's get back to the lower circuit, and you ask yourself a question: would there be any current through this resistor in such a way that no current should be passing through the galvanometer? So let me show you the pathway. So let's say the current starts from here, goes over here, flows through this resistor, goes down, and gets back to the battery. And what do you see? You see a complete continuous path for the current. So current would be flowing through that path, but since the current is not going to the right side, from that point the current is not going to the right side. So the galvanometer would be reading no current, but the current can flow in the internal path. The resistor that was here, in that case no current was flowing, because if you were trying to trace the path for the current, so let's say you started the current from this side, then you go over here, then you have to go to the negative of the battery one way or the other. So current goes through here, but then it has to pass, the current has to pass through the galvanometer. But since the galvanometer is reading no current, we have to say no current should be flowing through there. So we cut off this one, we cut off this one, and we cut off this one. So in this case, since current is flowing through this one, so these 1.5 volt, all of it 1.5 volt would not be provided against XP. So VXP is not equal to 1.5 volts, unlike example 1, example 2, and example 3. This time around, it won't be 1.5 volt. There would be some voltage drop. And since in the path of the current, there are two resistors which are included in the pathway, then we have to find the voltage drop. And if we find the voltage across this one, across 1 ohm resistor, that voltage would equal to the potential between XY. Why? Because this resistor is connected in parallel with XP. Check it out. The left sides are joined and the right sides are also joined for this resistor only. The two ends are connected directly. So we can say the resistor 1.0 ohm is in parallel to the point XP. So whatever the voltage is across 1 ohm would be the voltage across XP. And if you're thinking 0.8 volt is also parallel to XP, it's not. Because if 0.8 volts were parallel, then 2 points should be joined directly. For example, from here, these 2 points are joined directly, okay. But if you want to join X and the other side of the resistor, you have a battery in the middle. So there's no direct connection for this one. So you need to find the voltage across 1 ohm resistor. How do you do? Use cross multiplication. So resistance and voltage. So 1.5 volts. So let's get back to the same question. So 1.5, the total 1.5 volt is provided to the total resistance, which is 1.8. Connected in series, so you see 1 and 0.8 connected in series would be 1.8. So across the resistance of 1.0 ohm, how many volts would be provided? Okay, so this formula that we use, that we call cross multiplication, formerly it is known as potential divider formula, which is the same thing as the cross multiplication, but formally it is known as potential divider formula. Just let me hit it on the calculator. So what we get for this one is we get 0.836. Yeah, we get 0.83. So X equals to 0.83 volts. So what does that mean? The voltage across the 1 ohm resistor is 0.83 volts, and that would be the voltage between the points X. But you need to find the length. Once again, you need to find the length XP in all of these questions, in all of these examples. You need to find the length XP. So let us use the cross multiplication once again. So voltage over here, length over here. So for 2 volts, the length was 1 meter. And for 0.83 volts, the length would be X. And that in this case, 0.83 divided by 2, 0.42 meters. So what does that mean? The movable terminal P, the pointer has to be placed slightly below, slightly to the left of the midpoint. Only then you can have the potentiometer in a balanced state. So let's check out some of the other past paper questions of this topic. We'll try to wind up this one topic in this lesson. So here we have some of the questions that are from the topic of internal resistance and from potentiometer as well. So for example, here we have the first one. And so What we have is we have a 4 volt EMF of the battery is 4 volt, but it has some internal resistance, which means the terminal voltage of the battery would not be 4 volt, would be slightly less than that. The resistance of the fixed resistor is, I don't know how much, should be given 0.35 is the internal. XY wire has the resistance 0.90 volt. Okay, so this thing, the wire has the resistance 0.9 ohm, and we need to find the current through the wire. Okay, so current in the wire needs to be found out. You see, wire is also treated as a resistor. So if you want me to draw a simpler circuit, I can draw it for you. So this is your battery with 4 volts, and treat the wire just like a resistor. What is the resistance of the wire? It is 0.9 volts, sorry, 0.90 ohms. Then you have another resistor which has resistance R, we don't know how much is that. And then you have the third one, which is the internal resistance of the battery, which is 0.35 ohms. You need to find the current in the wire. And you know this thing, that the potential difference across the wire is 1.8. So the voltage across the wire is 1.8, and you can easily find the current. Voltage is 1.8 volts across the wire only. Okay, because out of these 4 volts, some of the voltage would be dropped over here, some of the voltage would be dropped over here, and the rest of the voltage would be across the wire, which is 1.8 volts. So current in the wire would be voltage across the wire divided by the resistance of the wire. Voltage across the wire is 1.8, resistance of the wire is 0.90, and if you hit it on the calculator, you get 2.0 amperes. So next part, you need to find the number of free electrons that pass through a point in the battery in a time of 45 seconds. So you have this formula, I equals to Q over T, or you can say Q equals to IT. And you also know this thing, Q equals to number of electrons or number of charges multiplied charge on each electron. Number of electrons times charge on each electron into I into T. Where do we study that? In the workbook of current electricity. Q equals to the total charge equals to number of charges times charge on each electron. If you want to represent number of electrons by small n, totally your choice, but the n here represents the number of electrons. So what is the number of electrons? Well, we need to find out. What is charge on each electron? 1.6. So n as it is, and the charge on the electron would be 1.6 into 10 to the power minus 19, and the value of current was 2.0, and time is given as 45 seconds. And if you just hit it on the calculator, you'll be getting 5.6 into 10 to the power 20 with no unit. Okay, because it is the number of electrons. And then you need to find the resistance of the unknown resistor, the capital R. That needs to be found out. So what do? We know the current passing through the circuit, and you can simply use this expression. There are like a lot of ways you can answer this question. So what I'm going to use is, I'm going to simply use the formula of current, resistors, and the expression that relates all three of them, V equals to IR, right? But then, do I know the resistance across this one, across the resistor R? It is, the voltage across R, we don't know. So I'm going to use the total voltage, and I'm going to use the total current, and I'm going to use the total resistance. So what is the total voltage of the circuit? 4 volts, because that 4 volts is supplied over here, over here, over here. But if you add 3 of them, the voltage of the consumers, it would be 4. So 4 equals to I, which is current is 2.0 amperes. It would be same through each component because all of them are connected in series. And the total resistance is, since we have taken total voltage or total current, then we have to take the total resistance as well. So the total resistance would be sum of this one, sum of this one, plus sum of this one, plus this one. So 0.90 plus 0.35 and the unknown, let's call it x. Simply find the value of x from here. You add all three of them, multiply by 2, and just hit it on the calculator. Would be done something like this. So 2 would be shifted on this side. It would be 2 equals to 0.9 plus 0.35, 1.25. So 2 divided by the answer, we get 1.6. Sorry, not divided by. Let me just do the calculation. It should be subtracted on the other side. So you have 2 over here. And on the other side, what do you have? On the other side, what you get is 0.9 plus 0.35. What you get is 1.25. 1.25 plus x. Now, for x, it would be 2 minus the answer, which would be 0.75. So the resistance would be 0.75. So let's move on to the next one, and which is a more important one because this is a question of the potentiometer. So what you see, matter of fact, it is the part C, I think. So in the same circuit, now we have connected a source of, we have connected another battery, but in this case as well, the EMF of that unknown battery is also given. But the question is, what is the total length of the wire? That needs to be found out. And they have given this thing as well, that the galvanometer is in the balanced state. The reading on the galvanometer is 0. And you don't have to find the length xp in this one. Previously, we were finding the length xp, but in this case, the length xp is given. And it is given as 0.30 meters. You can read over here. The distance xp is 0.30 meters. What we need to find is the total length xy. So the total length is around 1 meters, but it's not necessarily 1 meters. You need to find it. So if this thing is 1.2 volts, can I say the voltage across xp would also be 2 volts? Like the voltage over here should equal to the EMF of the battery. And we don't even have to compensate for the voltage drop. First of all, there is no internal resistance shown for the lower resistor, for the lower battery. And even if it were shown, it would have been ignored because the galvanometer reads no current, has no voltage drop in that internal resistance. So the voltage across xp is also 1.2 volts. But then the question is, what is the total voltage across xy? What is the total voltage across xy? It's not 4 volts. Because in the upper loop, the current would be flowing. And out of those 4 volts, some of the voltage would be dropped over here. Some of the voltage would be dropped over here. And only the leftover would be across xy. And matter of fact, in the question we are given with the voltage across xy, which is, if I scroll up, the potential difference across xy is 1.8 volts. So across xy, we know it is 1.8 volts. So now let's use the cross multiplication. So you write voltage on one side and you write length on the other side. So the total voltage of 1.8. Okay, let me write the other one first. The given one. If the voltage is 1.2, it was given for the length 0.3 meters. This one is in meters. Or you can think of it this way. For the length 0.3 meters, the voltage was 1.2. And for what length, which is the total length, you'll be getting the voltage 1.8. So for what length, which is xy, you get the voltage which is 1.8 volts. So we know the voltage across xy is 1.8 volts. So let us find the value of x from here. So x equals to 1.8 times 0.30 divided by 1.2. You hit it on the calculator and you get 0.45 meters. And you see, for this one, the lower battery, for which we generally have to find the EMF, but in this one they have given the EMF and they have asked you the counter question, what should be the total length? And in most of the cases the total length is given and it is generally given as 1 meters. But in this one they have asked you to find the total length. And the EMF of the lower battery is 1.2. There is no internal resistance shown, first of all, and even if it were shown, it would have been redundant because no voltage would have been dropped across that internal resistance because the current does not flow through the lower circuit. When I say lower circuit, I mean this one, because the galvanometer reads 0, so no current flows through the battery. The lower battery has no voltage drop across the internal resistance. And matter of fact, if you so length is 0.45. If you read the okay, then we have the next question. The fixed resistor is replaced by a different fixed resistor of resistance greater than R. Say and explain the change, if any, that must be made to the position P on the wire XY so that the galvanometer reading is 0. So this is a very interesting question. Very interesting one. The fixed resistor is replaced by a different fixed resistor of resistance greater than R. Okay, so I'm going to scroll up to the diagram and I'm going to remove all the extra details. Hopefully you have noted it down or taken screenshot. I'm going to erase it off. So the question is, they replaced this resistor. Let's say initially the resistance was 10 ohm and they replaced it with a resistance greater than that. So the resistance of R is now increased. Let's say it is increased to twice the previous one. What happens to the position of pointer P? In such a way that the galvanometer reading should remain 0. So if the galvanometer reading should remain 0, it means the potential difference between X and P should still be 1.2. It should still be 1.2. Only then the current through the galvanometer can be 0. So what happens by increasing the resistance R is that the voltage across X and Y would also increase. Or let me ask you that. Would the voltage across X and Y increase or decrease if you increase the resistance R? What happens to the voltage XY? The voltage across XY. If you increase the resistance R, the voltage across R would increase. Across R, it would increase. But what would happen to the voltage across XY? XY, just think about XY as an independent resistor. So if I just break down the circuit, if I could simplify it for you. So we have this thing, 4 volts over here. Then you have the resistor, which is 0.35. Then you have the resistor R. Then you have on the lower side, you have the wire for which the resistance is, we don't know how much resistance for XY. Okay, so XY has to be treated as a resistance. It is a wire, but it must be having some resistance. So you see, out of those 4 volts, if you increase this resistance, now this resistance would be getting more share of voltage compared to what it was getting previously. So out of 4 volts, let's say previously it was getting, uh, a matter of fact, we even calculated that. So let's say it was getting 1.5 volts. But if you have increased the resistance, now this one would be getting a bigger share. It would be getting bigger share of the voltage compared to it was getting previously. Hence, out of those 4 volts, if this one is getting a bigger share, now the voltage across this one would be decreased, because the other sibling now, he has to be provided with the bigger amount. So your mom, your father, they'll compensate by giving you the less amount. So xy would be getting lesser amount now, because the battery has to compensate for this thing. So voltage across x and y would decrease. So the total voltage at the wire xy would decrease. This is the most important thing. Now let's get back to the question about the position of the pointer. So in order to answer this question, let me draw a situation here, and that would be the last thing. So let's say previously the voltage across the entire length was, and it was given in the question that the voltage across xy was 1.8 volts. So voltage across the entire length was 1.8 volts. It could be something like this. You have, let's say, the total had to be 1.8 volts, and over here you have something like 1.5 volts. Over here you have 1.4 volts, and at this point you were having 1.2 volts. Over here you would be having, let's say, 0.6 and 0. Let's say 2, and over here you were having 0 volts. But that at the total length, at the end of the length, you were having, if you were using the total length of the wire, you would have been getting 1.8 volts. But only at the point P, you'll be getting 1.2 volts. But now the situation is changed. The total length of the wire will be having less volts, because there is less voltage across the wire xy. So let's say the voltage that the wire has now is let's say 1 volt now, only 1 volt. So you'll be having 1 volt over here. No, not 1, let's increase it to 1.5, let's say 1.5 volts. So 1.5 over here, probably 1.4 over here, probably 1.2 over here, probably likewise 0.8 over here, probably 0.4 over here, probably 0.2 over here, probably, and at the end you will be having 0. Now since you have to keep the current in the galvanometer 0, so the pointer has to move in such a way that the potential difference should be 1.2. So you see, when the overall voltage of the wire was decreased, then you have to move the pointer to the right side. So the pointer will need to be moved to the right side in order to get the same voltage. So basically in this case, your scale has been increased. Your scale has been increased. The same 1.2 volts, which was previously, let's say, at this length, at this mark, if the total voltage has been decreased, so your scale 1.2 volts would move slightly to the right side. So the pointer P has to be moved towards the right side. And how do you answer that? Well, you write all of it. I'm just writing the bullets. You can write the sentences. As the resistance increases, the voltage across xy decreases, and pointer needs to be moved to the right side. Okay, so the bottom line is, because the total voltage decreases, So the same value would now be shifted on the right side. If the total scale decreases, the same value would now be shifted on the right side. The second example,